And I actually remembered to hit record.
Professor, before you start, what exactly are we doing in lab today? Is it just a worksheet?
Yeah, it's the worksheet on sunscreens.
Oh, okay, cool. Thank you.
And I did post a digital copy of that because some of you like to do it on your electronic devices.
Professor,
I'm sorry?
Professor, there's no pre-lab for today, right?
Yes, pre-labs are only for wet labs.
Okay.
Okay, all of you have heard of enzymes. I think you probably heard about enzymes back in junior high, but a lot of people have heard of them, but they don't really know what they do. Enzymes are the bread and butter of making our body work. Without enzymes, we would be in sad shape. We'd probably still be a primordial soup, basically. So what an enzyme is a catalyst, and catalysts, importantly, speed up a chemical reaction by lowering the activation energy. So if we look at this here, and this is a measure of potential energy, and so this difference here is the energy Okay, so this difference between the energy of the reactants versus the energy of the product is whether it's absorbed energy or given off energy, is the difference between the reactants and products. Now, this hump here is called the activation energy. And this piece here is called the activated complex. So basically, when the reactant bonds are broken, so as we go through this process, reactant bonds are broken, and they're reformed. When they're reformed, they're either the reactants, original reactants, or products. Okay, so basically everything comes apart of the reactant bond-wise. We end up with this pool of unbonded atoms that are very high energy, very unstable, that want to become more stable. There's two ways to become more stable. You can reform the reactant, or you can reform the product. Depending on this difference in stability between reactant and product will be a ratio. And that's a ratio of product to reactants. And that ratio is called the equilibrium constant. And this ratio is temperature dependent There's a lot of things, but the ratio basically is very consistent based on the product and the reactants you're using. So you've got equilibrium constants with acids and bases and oxidation reaction, reduction reactions. Every reaction has an equilibrium constant. That equilibrium constant, again, is a ratio between the products and the reactants. If the equilibrium constant is greater than 1, then you have more products than reactants. So this is the So this is the thermodynamic favorability of a reaction. If the equilibrium constant is greater than 1. In other words, the products are favored. Okay. What this doesn't show is the kinetic favorability of the reaction. That is it slow or fast to reach? It's slow or fast to reach equilibrium. Let me give you an example of that. All of you have heard of a diamond. All of you have heard of charcoal. Those are one and the same chemicals. Vastly different. Guess which one of them that we have? Guess which one is more stable, the charcoal or the diamond?
The diamonds.
Yeah, diamond.
Charcoal is more stable. Weird, huh? The charcoal is more stable. That means that over time, the diamond is going to be converted back to charcoal.
I just have a question. Where did you post these slides? Because I don't see them under Unit 3.
Hold on. Let me check that really fast right now. Okay, it's there now. Sorry about that.
Okay, thank you.
Okay, so let's continue with this charcoal diamond example. Okay, so basically, charcoal is more stable than a diamond. I know it's weird. I would have thought the diamond was more stable a priori as well, but it's not. However, so this is thermodynamically favored. And kinetically unfavored. Okay, so what thermodynamically favored means is the charcoal energy is lower than diamond. Then again, unfavored means the activation energy is extremely high. It makes it super slow. So it's a weird dynamic. But it's a really cool example though, because everyone just assumes diamonds are forever. There's a song written about that. Obviously, Marilyn didn't study chemistry. All right, does this make sense, you guys? Okay, and this kinetic favorability is where enzymes come in, because enzymes will lower the activation energy. So if we had an enzyme that was tailored to this diamond charcoal transformation, we would see these very expensive pieces of rock go into charcoal. That nice investment, not anymore. Okay, so these two are fundamental in every single reaction in the universe. There's a thermodynamic component and a kinetic component. Every single reaction. Okay. I don't know if you touched on this as 305 or not, but it's really important. Okay, so let's go on here. All right. Enzymes, there's a whole bunch of enzymes, and they go from everything. For example, this is relative and general. Okay, so there's some enzymes that are very, very non-specific. For example, amylase. Amylase hydrolyzes carbohydrates. Proteases hydrolyzes proteins. Lipase works on fats. It works on just a generic group. Then you have absolute specificity and substrates. It doesn't mention that here. In the world of biochemistry, we don't have reactants, we have substrates. It's the same thing though. Absolute specificity means it only works on one substrate, not substance, substrate. For example, that would be, as an example, sucrase. Sucrase is an enzyme that hydrolyzes sucrose to glucose and fructose. You have that in your saliva. So as soon as you have 1 gram of sucrose, table sugar, it immediately forms half glucose, half fructose. So you immediately have fructose in your system, immediately, within seconds. The enzyme works very, very fast. And it's a form of an amylase, only it's very specific for sucrose only. So you have absolute specificity, relative specificity, meaning that it's more of a general reaction. And then usually there's some stereochemical specificity. This is a D and L difference. Okay, so whenever you have an enzyme reaction, they always list the substrate, product, and over the arrow is the enzyme that does that. Always in 3 parts. So this would be the conditions. Of the reaction. And of course, there's a pH and temperature component as well. pH depends on where the enzyme is designed to work. For example, if it's a protease, it's designed to work for pH 2 because it works in your stomach. If it's an amylase, it's designed to work around pH 7 because it's in your small intestine and in your saliva. So there's a pH always, and temperature always. And of course, temperature is horrendously important in enzyme activity. Excuse me. Regulation is a big deal in our body. We have positive feedback loops. And negative feedback. So for example, if we're all tanked up on energy, so what our body does is it looks for the amount of ATP present in our body. If the ATP is at a sufficient level, there is a negative feedback to produce less ATP. Or if we don't have enough, there's positive feedback where it creates more ATP, assuming the substrate is available. Okay. Frequently, enzymes require something else besides itself to work. And these are called cofactors. And they can be lots of different things. They can be an ion, for example, with hemoglobin that needs iron or magnesium. Cofactors can be either inorganic, like this, or organic. If it's organic, it's just called a coenzyme. So if an enzyme requires a cofactor, if it's not with its cofactor, it's called an apoenzyme. Okay. And of course, the coenzymes can be all kinds of stuff, vitamins, another protein, a polypeptide, all kinds of stuff. And you can see the variety here. Just all kinds of anything you can think of could be a coenzyme. Okay, so as far as the mechanism of an enzyme, so for the substrate to become a product, it has to bind with the enzyme and that's binding with the active site. Of the enzyme, forms the activated complex. In biochemical terms, that's called the enzyme substrate complex, but it's the activated complex. And then the product is formed and the enzyme is rejuvenated. So catalysts have to be rejuvenated. Otherwise, by definition, they're not a catalyst. So this enzyme here, enzyme E, is exactly the same as enzyme E over on the product side. If it's something else, it's not, then this reaction was not enzyme catalyzed. Now, it doesn't matter if it's an organic catalyst like an enzyme or an inorganic catalyst like platinum or magnesium or something like that. Okay, there's a whole bunch of mechanisms. There's extremely complex enzyme mechanisms, and basically it's the stereo conformation information of the active site on the enzyme. But basically, we have two kinds of sites, and we're going to get into more detail on this as we progress through this talk today. One is called the lock and key theory, and the metaphor is just like a lock, and you have one key that fits it. And that active site is perfectly aligned to the substrate. Once the substrate and enzyme become one, it's called the enzyme substrate complex, which is the, again, activated complex. Okay, and this is how we get the extreme specificity of enzymes. It's because the substrate molecule has to fit perfectly in the active site. Otherwise, nothing happens. The other general theory is called the induced fit. And basically, the active site conforms to the substrate. And there's varying degrees of this now. Some of them are very picky, some are not picky at all. Oh, let's see. I'm just reading the chat. Okay. Now, enzyme activity is called kinetics. Okay, that is the speed turnover number is looking at substrates converted to products. The enzyme international unit is just it's like the mole, only it's standard SI unit. Okay, and then an assay is a way to measure this activity. Frequently in biochemistry labs, you do these kinds of things. Our labs don't have a lab like this, but frequently they do. Now, these turnover numbers vary horrendously. Horrendously. Goes from, for example, 36 billion down to 900. Huge numbers differences. And it's just built into the reaction. Activation energy has a lot to do with it. Okay, so when you study chemical kinetics in either OChem or inorganic chem, like 401, for example, or 420, you talk about kinetics, what affects the speed of the reaction. So we have the enzyme, so this would be the catalyst concentration. The more catalyst there, faster the reaction will go. So the concentration of the enzyme is directly proportional to the speed of the reaction. Did you guys study the square brackets in 305? I've never taught 305, so I'm not sure what you. Okay, square brackets means moles per liter. Okay, so the concentration in the enzyme is directly proportional to the speed of the reaction. Higher the concentration in the enzyme, faster the reaction. Okay, same with substrate. You got more reactants, reaction goes faster. And then this varies. You can speed up or slow down the reaction by changing the, so there's an ideal solvent, ideal pH, ideal temperature. Swaying from any of those slows the speed. So deviation from ideal conditions slows the reaction. Okay, so if we increase the enzyme, speed up the reaction. Increase the substrate, increase the speed of the reaction. And if we change from the ideal conditions under which the enzyme is designed to work, in terms of its conformation, its active site conformation, all that stuff, the speed of the reaction slows down, frequently a lot. Okay, so that's what this is. This means a direct relationship between speed and enzyme concentration. Okay, so that goes back to now. This can't go on forever. So what happens is when you reach with a active site When the active site becomes overloaded, it can't turn over the substrate to the product anymore. You've got to clear some of this out, and that's what this graph shows. So your speed will plateau. It cannot go any faster than a certain amount. So it depends on the enzyme totally. Okay, so these are the factors that affect the speed of the reaction. Temperature changes the conformation. Of the active site. So does pH. So does salt. Solvent, though, is mostly bodily fluids. So it's mostly in an aqueous or a water environment. Physical movement, that's things like temperature and physical movement are closely related. But physical movement means you smash the enzyme, physical agitation, etc. And basically you go back up to changing the conformation of the active site. It all goes back to that. Active site, active site, active site. Okay. Okay, the active site conformation is directly related to optimum temperature. The active site changes the optimum by changing the temperature. The rate will change dramatically. And this depends on the situation. It could be a very steep curve or it could be a very broad one. So it depends on the combination. Same with pH, exactly the same thing. You've got an intermolecular force. And that intermolecular force will interact with the amino acid functional group and will change the shape of the molecule, which also changes the shape of the active site. It's kind of like what we talked about Wednesday on one of our proteins, and we had the solvent polarity versus the polarity of the side groups on the amino acids. Here's a series of here's good old sucrase we just talked about. You can see the most of the time we're looking at around physiological pH of around 7-ish. Talking about stomach stuff, pH of 2 or so. So the enzymes are very, very, very sensitive to pH changes. Okay. Inhibitors are a really important topic to talk about in terms of enzyme regulation. Excuse me. Okay, and you've got different kinds of inhibitors. Some are irreversible and some are reversible. It just depends. frequently poisons work by shutting down enzymes. Antibiotic shutting down enzymes. That's why shutting down enzymes, and we take antibiotics to fight off bad bacteria. We also kill off good bacteria as well. We also kill off our own enzymes. So taking a lot of antibiotics is not good. I try to not take any antibiotics unless I can get away with it. Okay, so okay, so heavy metals, they tend to bind with the cysteine amino acid. Early penicillin typically interfered with cell wall construction. Basically, the bacteria would just basically leak, and then it would cease to function. And penicillins over the decades have changed because of the issue of bacteria becoming resistant to them, just drugs in general. The inhibitors, usually when you say irreversible, usually there's something that's covalently bound. And the covalently bound and proteins are very, very strong, and they tend to be very difficult to break. Like when you have a permanent, you have to have very strong reduction agents and oxidation agents to break that covalent bond between the two cysteine amino acids. You've all heard about cyanide being extremely toxic, and yes, it is. It messes up cytochrome oxidase. It covalently binds with it, forming a very stable complex, and that oxidase doesn't function anymore. What does this look like to you guys? I know some of you have had A&P. What is this?
Cell membrane.
Yes. What else?
Is it an electron transport chain?
Yep. Yeah, it's carbohydrate metabolism, and it's the third cycle, not the third cycle, the third phase of metabolism of carbohydrates. This is electron transfer. This is where you get a big portion of ATP produced. And this is what cyanide messes up. Okay, so we have a lot of ways to inhibit the rate of an enzyme. One is to have something that competes with the substrate for the active site. So once the inhibitor is in there, the substrate can't fit in there anymore, and hence the reaction doesn't happen. Sometimes they're reversible, and sometimes they're not. So this would be a competitive inhibitor. And this would be an example of that. Okay. Now there's also a way to compete, and that is by having the inhibitor affect the active site itself. They'll change the conformation of the active site. Notice the active site here and here aren't the same. That's because when the inhibitor attaches to the protein, it modifies the site, the active site. Hence, the substrate, again, cannot fit in there. Okay, this gets into allosteric regulation of enzymes. It can be an activator or inhibitor. So going back up here, if the active site looks like this, and then you get an activator on there, it actually changes the shape of the active site so that the substrate can then fit in there. Or it changes it so the substrate doesn't fit in it. So one can be an inhibitor, one can be an activator. That's what this diagram is showing. Okay, so in this case, it's inhibiting. You have an allosteric inhibitor fitting into this spot, which is like an active site. It's not called an active site, but it's like an active site. It's very specific to the inhibitor. So the allosteric inhibitor fits into that site, and then it changes the shape of the active site. So the substrate no longer fits in there. And these are some examples. You don't have to memorize these examples. Just this is what I want you to know. This here, this diagram. Okay. And the opposite is we have an active site here that doesn't, the substrate doesn't fit in there, but when we have an allosteric activator, it actually changes the active site so that the substrate then can fit in there. So this would be an activator. Okay, so enzyme induction. This is a form of it's a form of positive feedback. In other words, if something needs to be done, the enzyme is then synthesized to do that. Okay. So you need to be able to distinguish between irreversible, reversibles, and then the two types. So this would be allosteric regulation. Okay, that's what I have on enzymes. So are there any questions in general? Unit 3 is going to be much more general than units 1 and 2, except for the beginning of Unit 3 where we talked about amides and proteins. When we get into the biochemistry, it's more general, good and bad. So, all right. One thing I want you to know are the classifications of enzymes. And in your book, it is on. Your book does a good job on enzymes, by the way. It's on page 590. It talks about the classification of enzymes. I'm going to post that. For example, you've got oxidases, reductases, dehydrogenases, transaminases, kinases, and you need to know these classifications because they basically will do really magical things. For example, there's a syndrome that some people have where they cannot detoxify ethanol in their liver, and it has to do with the inability to take the way ethanol is detoxified in your liver. There's an enzyme called alcohol dehydrogenase, and it takes the ethanol and converts it to ethanal, the aldehyde. Then there's another enzyme called aldehyde dehydrogenase, which converts the ethanal to acetic acid. And then that acetic acid then leaves your body via urine. Well, if you cannot detoxify the aldehydes in your body, they're very toxic. And that's a genetic condition. And there's a whole bunch of people in the world, about 500 million, that have this condition. But you need to know what a dehydrogenase enzyme does. And that is basically it. It oxidizes. Dehydrogenase means it removes hydrogens, which means that's an oxidation process. But anyway, I'm going to have a list posted in files on that. So you need to know those. Okay. All right. Any other questions about the new assignment I put together? So make sure you get the